Good morning everyone, we'll be starting class in 1 to 2 minutes time. Good morning again, and today's lectures are going to be focused on the continuation of the spectrum analysis topic. In particular, the first lecture that we're going to be doing today is referred to as the STFT, which is the short time Fourier Transform. And the STFT is particularly used for real-time signals for you to get an estimate of what the actual Fourier transform of the signal would be if you had the entire signal. The second lecture we're also going to be doing today is referred to as power spectral density, or PSD, and this is how do we go about calculating the average power for any signal once we have its frequency domain representation being the FFT of the signal. Alright, so and after we do these two lectures, I realized that from a query from one of your colleagues that question 5 and problem set 1, the solution actually is wrong, so I'm going to be redoing this right after the lectures and giving you guys the correct solution and the correct reasoning as to how you could go about formulating the solution as of such. Alright, so let's get started on today's lecture. So far, when we've been doing the fast Fourier transform, the FFT, we've been doing it on entire signals, where we had all the signal content to begin with, and we could just perform the FFT for the entire thing because it's referred to as a stationary signal where it does not vary with respect to time. Basically, the FFT works well for stationary signals because you have all the content of the signal up front. But when you're dealing with real-time signals, which are referred to as non-stationary signals, where the information comes in time intervals, the FFT doesn't work as expected because it comes like you only have a part of the signal. So as such, when you do the FFT on that part, you only get only the frequency content for that part, and you don't know how that particular part of the signal applies to all the other parts of the signal when you actually do get the entire signal itself. There may be some cases where, due to hardware limitations, you can't store the entire signal because the memory constraint is just too large, and you only have a finite amount of memory to deal with. So you would have to figure out, okay, how can you actually process the signal in real time and continuously process it while managing your memory requirements as of such. So these kind of techniques that are being formulated for non-stationary signals, they differ greatly from the general technique from when you see it with the entire stationary signal and you can just perform the entire FFT on it. However, there's a little bit of similarity with, yes, you do still perform the FFT, but the FFT is going to be applied in a different way for non-stationary signals in particular. Now, we are using the definition of stationary and non-stationary signals here in a very loose manner, meaning that stationary signals is we have the entire signal, like if it's pre-recorded, And non-stationary signals means that we'll be having the signals coming in intervals of time, being it's a real-time signal. But there is a more rigorous definition of stationary and non-stationary signals if you're doing the communication courses as such. But for our purposes, a stationary signal is a recorded signal, a non-stationary signal is a real-time signal. So if we watch a general example speed signal here, and let's say it was coming in at every 100 milliseconds, this frequency content here will be varying over the time when we'll be able to get it in particular. And this sort of signal here is also aperiodic in nature. So in order to analyze these non-stationary signals, we need to use a sliding time window. And that goes back to the content that we learned in Monday's lectures, where we had windowing techniques, how they actually can be applied to aperiodic signals, since we don't know the period of the signal to begin with. So for each part where the window is applied, we apply the FFT for that particular instance, and we'll get the frequency content for that particular time, and then we slide the window to the next part of the signal, and we just keep on repeating the FFT process until we cover the entire signal entirely. And this process is what we refer to as the short time Fourier transform, or the STFT of the entire signal. Now, the example I've given you here is where we actually do slide the window across the entire signal. The opposite can happen where we hold the window stationary, but the signal slides across the window instead, which is typically what happens in a real-time system. So we define our window and its size and so forth and what shape it takes, but then the signal slides across the window, and for each interval the signal slides across the window, we calculate the FFT accordingly for that particular slide, and then we repeat the process for all other slides that do occur within the signal itself. So the general example here is, well, we have our signal and then we have our rectangular window here. Please note, for the example I'm saying rectangular window, it's possible to use triangular windows, Hamming windows and so forth because they're more practical. We saw the reason not to use the rectangular windows in Monday lecture is because the side lobes were fully attenuated, resulting in unwanted harmonics. But just for this general example, we'll be using a rectangular window to illustrate our purposes. So we define a window here and the window size and width and so forth. And then for this particular instance here, we calculate the FFT. And then as the window itself slides across the signal, we keep on calculating the FFT for each slide as it keeps on going here, until we cover the entire signal itself. The opposite can happen, where we hold the window here constant, and the signal slides across the window instead. And for each slide, we calculate the FFT as well. So in formulating the window here, we need to have the window size here, which is referred to as capital NW, and the sliding window being the shape of the window itself. So our particular case here, we're using a rectangular window, but like I said, it's possible to use different types of windows that we saw in Monday's lecture, being the triangular window and the Hamming window, the Blackman-Harris window and so forth. You can choose which window you want to use. So each result obtained using the STFT, you will get three characteristics, which are going to be time, frequency, and amplitude. And it's possible to display each separately or combine all three of these characteristics into a spectrogram, where the axes will be time and frequency, but the amplitudes vary with the color intensity or the different colors in particular. Now, a spectrogram is not to be confused with a plot. A spectrogram actually is an image. And this here is a general example of a spectrogram, where the y-axis here is in terms of frequency, the x-axis here is in terms of time, but for each color intensity that you have here, depending on the shade of the color, represents the amplitude of the signal itself. So if we watch the x-axis itself and the color axis here, that x-axis and the color axis will give us the amplitude versus time, Similarly, if we watch the y-axis and the color axis, we get the frequency versus amplitude as of such. And if we just watch the x-axis and the y-axis, we get frequency versus time and so forth. Now, spectrograms are widely used for audio signals in particular because it helps us quickly identify different characteristics of the signal immediately. So, for instance, if we watch the frequency axis here for these two spectrogram plots, you can see here that most of the frequency content is centralized around like from 0 to 4000 Hz. But then the frequency content here for this particular plot is centralized between 0 and 6000 Hz, closer up to the 8000 Hz mark. And just from analyzing these two, knowing that this is the spectrum that word hello spoken by two people, we can tell here that the left spectrogram is spoken by a male voice, and the right spectrogram here is spoken by a female voice. The reason for this being is that male voices tend to carry lower frequencies, and female voices tend to carry higher frequencies. So just from watching the spectrogram alone and watching the frequency axis, we can determine that in particular. The time axis here just gives us an idea of the instance in time which the word hello has been spoken. And as well as, if we watch the color intensity here, and I know there isn't a color axis here, we can see here that the more red in the signal here, and we're making an assumption here basically, is that the red part of the signal means that it's a higher amplitude intensity than the green part of the signal itself. So we can see here for the rightmost spectrogram, which is a female voice, that the intensity of the signal here, being the amplitude of the signal, is quite high. So meaning that the woman who spoke this in particular here spoke this very loudly. Whereas for the male voice here, the intensity here was a little bit lower in particular in comparison. That meaning that because of the lower frequency, there was a lower amplitude in particular for that male voice, so he didn't speak quite as loud as the female voice. So we can extract all that information here just from watching these spectrograms in particular. So, like I said, when we were watching the sliding window illustration, you can use any different type of window in particular. And the reason why you don't really use rectangular is because of the side lobe attenuation factor that we saw in Monday's lecture. That the rectangular window, because of the shape of the window, the transitions are very abrupt. And when we saw the frequency domain representation of the rectangular window, we also saw that the side lobes in particular weren't attenuated properly, resulting in unwanted harmonics. So in using other shape windows like the triangle, the Hammond, Blackman-Harris, and so forth, you tend to mitigate all those side lobe frequencies in particular a lot better than the rectangular window. Because of the different shapes of those windows, when you are watching to calculate for the width of the window, it's always going to be at the base of the window itself. Not at the top and not at the center, it's always going to be at the base. So the maximum width of the window that you could calculate for, that's going to be NW in particular. The shape of the window is going to be defined by the window equation. So like, for example, when we had our Hammond window here, the equation for that Hammond window was given by, let's call this WN. It was 0.54 minus 0.46, and then cosine of 2 pi k on n minus 1, if I remember correctly. It was something of that nature, and that would actually determine the shape of the window itself. Also, when you're sliding the window across the signal, for each sliding factor, so to say, typically you make sure that the window sliding factor, it's going to be half of that of the window's width. And this can actually be adjusted depending on the window's type, because you do want some sort of overlap to occur instead of having independent slides that don't have no overlap altogether. The reason for this being is that when you do have this overlap factor, you tend to cover more of the signal in particular, instead of having it separate in particular. So like, let's draw a quick illustration here to show what I'm talking about. Let's say if we had our random signal here, and then we had our window here, but then we had the window here again. This part we're going to be missing entirely because of the window shape and for each slide. So that's why it's important to have an overlap factor to make sure that you do capture this missing information in particular. It's also quite important as well because when you do have that overlap factor, it also recalculates the FFT for each window slide. And when you do formulate the entire result, it gives you a better accurate representation than just having one instance where the FFT was calculated as of such. Because now that means you calculate for FFT for this part here in particular, considering the information on the left hand side, or where you have the overlap, you can now calculate the FFT considering the information on the right hand side. So in factoring those two parts of information, you get a more accurate representation of what the FFT would be for the entire signal. So that's why the overlap factor here is quite important, because you capture any missing information as well as you get a better accurate representation of what the FFT would be for the entire signal. So in trying to determine the frequency resolution, that's going to also be set by the width of the window, being the number of samples that you tend to take. So the calculation for that is going to be delta FW equals to the sampling frequency divided by the window's width. And this will actually determine the resolution of the entire STFT that you're doing in particular. As a result, if the windows, since the window's width here is going to be less than the entire width of the signal, that means the frequency resolution for the STFT here is going to be less than the frequency resolution of the entire signal. So what that means is that the frequency resolution for doing the STFT is decreased, and as a converse, because frequency is equal to 1 on time, the time resolution increases as a result. Now the STFT, if you actually do want to apply it to any general audio signal or any type of signal that you have in particular, the function for this in MATLAB or Octave is referred to as the spectrogram, and this is basically the format of the function itself. So the first input to the function here is going to be your time signal data, being x. The second part is going to be the window type and the size. So in this particular case, we were using a Blackman window with a size of 512 samples. The third input here is going to be the overlap for the windows. So we said, okay, we wanted to have an overlap of NW divided by 2, so which that's going to give us 256 samples. The fourth input here is going to be the size of our FFT. So because we're dealing with 512 samples, we match that to the FFT as well. So we use 512 samples for the FFT. And the final input here is going to be the sampling frequency. And the sampling frequency is going to be reflected onto the X data that we had from respect to time. All right, so that brings us to the end of our first lecture for today. Are there any particular questions on the STFT? The overlap size is not always going to be half the FFT size. Typically, when you're using windows, different types of windows, they do give you a suggested overlap. So there may be cases like for the triangle window, which tends to be a lot more pointy in nature, they tend to have a higher overlap factor because you're trying to cover the entire signal in particular. So in such a case, that means that you might be going like 0.7 or 0.8 in particular because you're trying to make sure that you don't miss any information. Whereas for like the Hammond window and the Hannon windows and Blackman Harris and so forth, because of the general shape, you still manage to capture a lot of information regardless, so you can have a lower overlap factor in particular. The overlap size is not really like padding, so to say. It's not introducing additional frequency components. What you are trying to do is to make sure that you do cover all the frequency components that you would have gotten if you had the entire signal to begin with. So it's just to make sure that you don't miss any information, that you don't miss any information while the signal is coming in for each time interval. Because if you do miss information, then you don't capture that frequency content altogether. And you also want to make sure that when you are calculating the FFT, remember the signal content, you will have the left of the window and then on the right of the window wherever the overlap does occur. So you want to make sure that you factor in both sets of data when you're calculating the FFT for that particular overlap to make sure that you do calculate the correct frequency content in particular for that part. Because if you only consider only the left-hand side of the data, that's only one half of the data you're dealing with. You also need to consider the right-hand side of the data for the overlap to make sure that you get the correct thing in particular. With the triangle window, that's why you need to have a high overlap factor. You will still miss like parts of the signal because of the general shape, but remember when we were doing the triangle window, and let me just backtrack here a little bit so I guess an empty slide. When you're doing the triangle window in particular, remember it wasn't a pure triangle like this. It was like something like that in particular. And only when you went up in samples, then you'd approach closer to this. So as n increases. So it's possible for us to have like a really huge overlap factor, such that the triangle here will go like that and that. But then you still miss like something here in particular. So yes, it's possible that you can miss. So that's why the triangle window, you tend to have a really high overlap factor to try your best not to miss this data. Because if you have a low amount of samples and you're dealing with this here in particular, then your overlap factor here tends to be a lot easier to factor in, because now you can go here like that and so forth. And like you can go here like that and so forth, minimizing the overlap factor in particular. Because remember, the characteristics of the triangle window was such that the maximum amplitude gets as close to 1 as possible, and the minimum amplitude gets as close to 0 as possible. And as you increase the number of samples, then you keep on approaching closer and closer to those. So the number of samples you use for the triangle window, as well as the overlap factor, do play an important part in its usage for the STFT. All right, any further questions? Alright, it doesn't seem like we have any further questions, so let's move on to the second lecture for today. Alright, so, oops. Right, so our second lecture for today is referred to as this power spectral density, and this is important for us to calculate the average power of any particular signal once we have its frequency representation via the FFT. And we're going to be watching an actual mathematical technique that we can use here to calculate for the average power of any signal once we do have its FFT representation in particular. So in continuous time, if you wish to calculate for the power of the signal, being the average power of the signal, you've been using this integral formula here, which will mean average power is equal to 1 divided by the periodic time, or the estimated periodic time, integrating with respect to the periodic time of x of t all squared with respect to dt. And this sort of integral process tends to be pretty long and tedious to do, because especially this x of t here being all squared, the integral tends to get a little bit complex in particular, especially when you're dealing with sine and cosines. So this method, it's not really easy to do automatically. So, and using the DFT or the FFT here in particular, we're able to transform this equation here into a numerical component equation, instead eliminating the integrals factor and making the analysis a lot easier. And in order to do this, we make use of Parseval's theorem, which basically states, this being the long definition here, the short version here is that the power in the time domain is basically the same thing as the power in the frequency domain. That's basically all what Parseval's theorem tells you. Anything, the power in time is equal to the power in frequency, and vice versa. So, for continuous time signals, you'll have all these integral formulas here with respect to time, and it can also be mapped with respect to frequency and so forth. But for discretized time signals, this is what we're going to be using. It's just basically a summation series, where in time it will be an x of n squared with respect to delta t here representing our time interval. But in frequency, it's just going to be the summation of each one of the frequency components squared with respect to the frequency bin space, delta f. And we're going to see a practical example of this in a little bit. So the general transformations is that from moving continuous time to discrete time, all integrals have been transformed into summations. Instead of having the sample time interval being delta of t, this is now going to be the bin space in delta of f. Delta of t here was 1 divided by the frequency, the sampling frequency. In bin spacing, that's going to be the sampling frequency divided by n, being the number of samples that we had in particular. And xm squared is just going to be the magnitude of squared of the x of m signal, where x of m is going to be of frequency content of the signal. Now, in doing the power spectral density here, I'm going to observe why in particular in the next few slides. We're only going to be considered with the signal content from 0 Hz to half of that of the sampling frequency. And you want to see why in particular this is important, and why we don't need to consider the entire signal itself. So, explain this textually here on slides. Basically, the frequency content itself of the entire signal can be represented from 0 Hz to half of that of the sampling frequency. And this being such that there's a symmetric property that we observe with the FFT in particular. So let's visually examine this to see the symmetric property. So we're going to consider a generic x of n signal here, given by this vector of values, and we get know the sampling frequency here. And we can use MATLAB here or Octave to transform this x of n signal into the FFT version of itself. We can multiply by delta of t and get the absolute values as of such. So when we actually do plot this, we see here that we get our instances where for each bin spacing, where our bin spacing here is going to be 10 hoods, we have some amplitude associated with these by the absolute values itself. And what we can see here is that at 0 hoods, this node here at 0 hoods is what we refer to as the DC component of the signal. But for all instances afterwards, these are going to be the frequency or AC components of the signal itself. If we watch around FFS divided by 2, because FFS was 80, so half of that's going to be 40 hoods. If we watch the left of the signal here and the right of the signal here, ignoring this DC component, we basically see that it's a symmetric version around this 40 hoods. So this 30 hoods here and 50 hoods have the same amplitude, the same thing with 20 and 60, and the same with 10 and 70. So the frequency vector here does make sense, because FFS here was equal to 80 hoods, half of that is going to be at 40 hoods here, and delta of F is going to be spaced at every 10 hoods here in particular. And because of the symmetric property around FFS divided by 2, these magnitudes here are basically repeated because they were complex conjugates of the other in the imaginary values instead of the absolute values. So it was like such that it would have been like, if you considered the FFT values being not the absolute values, you would have got something like 3 plus 2j, and then you got 3 minus 2j here. And in calculating for the magnitude of each one of these, it's going to be the same thing. So that's why you can actually see the symmetric property here, because you're actually dealing with absolute values instead of the actual complex values themselves. And the symmetric property of this being around half of that with the sampling frequency means that these values here are basically repeated because they are just mirrored around this 40 hoods. So we can't just get rid of these parts here on the right hand side, on the left hand side, because they also contribute to the power of the signal. So what we end up doing is that we just multiply this part of the signal here by 2. Comes like we just add the two signals together themselves because they're just the same magnitudes. And as of such, that means that we'd still preserve the power of the signal entirely, because this here being FFS divided by 2, the 30 Hz and the 50 Hz are the same magnitudes and basically the same frequency content if you want to be like the first or second or third sidebands. So these basically are maintained accordingly when you're doing the absolute values here for calculating the power of the signal. So in formalizing the power spectral density function, the shorthand version for this, and we now just basically don't have to factor in the entire huge summation process, is that we're considering this be equal to Gxx, representing the power spectral density of any signal, is equal to 2 divided by T multiplied by the modulus of x of m all squared, but the modulus of x of m is going to be the absolute values of x of m itself. And this just means that where m goes from 1 to n divided by 2 minus 1, that means we only consider for half of the signal itself. And remember that because we're taking the magnitude squared here, that's basically going to be the same thing as we took the absolute value of x of m and then we just squared them in particular. And the reason why we have 2 divided by t here is because we're going to be factoring the power on the right hand side of that f of s divided by 2 onto the left hand side of f of s divided by 2. So that's why we have this 2 here in particular for our formula. So that means instead of having the entire signal itself to calculate for the power, we just have the DC component here and then 2 times that of the original AC components that we had for the signal itself. So power spectral density, this is the formula that you're going to be using in particular. 2 divided by T multiplied by the magnitude of x of m all squared here in particular. These units here for this power spectral density formula is going to be volt squares divided by seconds or volt square hoods in particular. So it's also possible for us to mathematically represent our Parseval's theorem with respect to the number of samples in discretized time mapped into the frequency domain representation here. But this is basically a mathematical proof, and this is for anyone who wants to do a little bit of further reading as to how the proof exists. This is the formula that satisfies the proof that the power in the discrete time domain is equal to the power in the discrete frequency domain as of such. And for any unwindowed time series, it comes such that if we're trying to find RMS power instead of the average power in general, we need to take gxx of f of naught multiplied by the bin spacing delta of f, and we need to find the square root of that in particular to get the RMS power. So power spectral density, as we observed it here, works for stationary signals. For non-stationary signals, there are other methods to calculate the power spectral density, but we're not going to be focusing on that in particular because those mathematical formulas tend to be a little bit complex in nature. And they do rely a lot on using statistical modeling of the particular signal, and you do have to factor in the averaging and the overlap factors used for the STFT that we saw in the previous lecture in order to calculate accurately enough for the power spectral density of a signal, because remember, that's dealing with real-time signals, so it comes like you keep on estimating for each area and every slide of the signal when you're doing the STFT. So calculating the PSD for non-stationary signals is not part of our curriculum. We're only concerned with calculating the PSD for stationary signals using this method that we saw here. All right, so that brings us to the end of the power spectral density lecture. Are there any particular questions regarding the material here? Alright, doesn't seem like we have any questions for power spectral density. So just remember, when you are calculating for power spectral density, this 2 divided by t here, this t here is going to be referred to the time of the periodic time of the entire signal in particular. X of m here is referred to as the frequency content of the signal itself, such that you do need to make sure that you do the Fourier transform, the fast Fourier transform of the original x of n signal here to get x of m, and then obtain the magnitude values accordingly and square them with respect to the bin spacing that you use in particular. So just remember that the t here is referred to as the periodic time, or the estimated periodic time. X of m here is going to be the frequency content of the signal that's going to be squared in particular. And the reason why we have 2 here is to make sure that you only go from 0 to f of s divided by 2 in particular. Alright. So let's keep this. Alright, so we're moving on to problem set 1 revision here in particular, and this is going to be the correction to question 5, which I did because after a query by one of your colleagues, I realized that the explanation that I gave you guys for question 5 it was wrong, as well as part of the solution I also posted up, it was also wrong, and I'm going to explain to you guys why it's wrong and how we're going to go about correcting it in particular, and seeing the reasoning in this particular question as to how we can formulate our solutions. So let me bring up my whiteboard here. There. Right. So we're going to do basically a quick sketch here to illustrate our problem that we had. Right. So we know that for the x of n sequence here, in particular, the start index was at -5 and the final index here was at 14. The start index had a value of 3, the final index here being 14 had a value of -4. So let's actually draw a visual representation of this. So we'll be here at -5 and 14, and we know here that at -5 it was 3, and at 14 here was -4. This here would be our x of k signal accordingly. Now the reason why I'm saying this is x of k, y of n here for the convolution, because we're going to be convolving the signal with itself, is x of n star x of n, and this basically would be such that it's y of n here is equal to the summation towards infinity of x of k multiplied by x of n minus k, where we actually do this with respect to the convolution equation. That means that we need to make sure that we also have the x of minus k signal that's going to be flipped. So that means when we flip the signal here, instead of 14 we're going to have -14 on the left hand side, and we'll have +5 instead of -5 onto the right hand side, which is going to be x of minus k. This here is going to be -4, and this here is going to be 3. Now, if we watch our overlap factor here, and we're just going to draw an illustration to say, okay, this part here is going to be at 0, and we can see here that when we do our slide in particular, we need to consider this -5 here and this +5 here. So if we draw our -5 here in particular, representing the initial slide from the x of k signal, so this is going to be like if we take the x of minus k signal here. So I'm going to draw this again, and I'm going to draw like a huge plot here. So this comes like we take our, let's see, our x of minus k signal here. So it's going to be like from here to here is x of minus k, because this is going to be our sliding signal for our convolution. And then we say here it's going to be at -5 for our x of k signal here, going up to 14. So this is like before the signal itself actually slides. When we do slide the signal entirely, because it comes like if we're doing the slide one by one, it will be such that we'll be going that for the x of minus k signal, erase that. It'll be such that it'll go here first and be like, okay, this is going to be at 5 here, and then 5 will be here, but then the match-up point here will be -4. I would say like -2, and 2 here, 5, and so forth. So we can keep on going here. Then this the 5 of this x of k signal will come at this point. Same thing here. 5 will now come here, and 5 will come here as we keep on sliding. So what we're going to observe here is that in doing all these slides, and we're going to consider that we started at -5 here, and this factor here for the slide is going to be +5. That means we have an overlap factor here that we need to calculate for to get our starting index. This overlap factor here is going to be such that we see that it goes from +5 here to -5, but we need to factor in that 0 value. Reason for that being is that, let's say if we went in between -2 and +2, you might say, okay, it's going to be -2 and +2, so there's going to be 4 values here in particular. But that's wrong, because you have -2, -1, 0, 1, and 2. So in reality, this here is actually 5. So it's not going to be magnitude of -2 plus 2, which will give you 4. Nope, that's entirely wrong. That's the wrong thing. It's actually 5 values in particular. So it's going to be -2, the magnitude of -2 plus 2, and then you have to factor in that 1 additional value here to get 5, which is correct. So our overlap here that we're calculating for when we do this, when we need to get our start point for y of n, the equation for this is such that it's going to be the start point. Okay, let me put this in. This is going to be the start point for x of -k now remember this here sliding from left to right multiplied by the start point, sorry, not multiplied, add start point for x of k. I remember this here is stationary, plus 1. And we're going to be considering these accordingly as of there. So the start point for x of -k here, when we watch our sketches, the start point here, because this is sliding from left to right, that means the start point is going to be on the right. That's going to be 5. And then we need to factor in the start point for x of k. Which is going to be at -5 here, but we're only be dealing with the magnitude in particular. Modulus of -5. And then we need to add in that 1 to consider that 0 overlap. So we get here being 11. Now, however, when we visually watch where our start points do coincide when we start doing the convolution, it was as a negative index. So, because it was at a negative index, start point for y of n is at a negative index. So that means n here is going to be -11 because we have to factor in that negative index. So that's how we get this being the start point here being y of -11 in particular. Then similarly, when the question asks what's going to be the value of the first what is the value of the first non-zero value in the convolution, That's just going to be 3 multiplied by 3 here, which will give us a value of 9. So y of minus 11 will be 3 multiplied by 3, gives us a value of 9. So this is part B. Let's go back up here. This is part A. So we can see here, this part was a value of 3, and this part here was also a value of 3. So we just multiply the two together, that's how we get the value of 9. Now for part C here, which we also need to figure out in particular, oh whoops, I'm totally labeling these wrong. It's Roman numerals. Okay, so I'm going to relabel these. This is part 2, 3, and label this here as part 1. So for part 3 here, we need to figure out what's going to be the length of our sequence, right? So the length of our x of k sequence is going to be equal to our start point of x of k plus our finish point of x of k plus 1, because you need to consider that part where we go across the 0 value on the x-axis. So we're only dealing with the magnitudes of the x-axis here in particular, so that's going to be, when we scroll back up here, 14 and minus 5, we're going to be taking the magnitude of minus 5 here, so that's going to be 14 plus 5. So this is magnitude of minus 5 plus 14 plus 1. That means we have 20 samples for x of k. And for the length of y of n, which is the result of the convolution, this is just going to be 2 multiplied by length of x of k minus 1. It's going to give us 39 samples. So let's illustrate this a little bit to explain why we get this. So let's say in our particular case, if x of k here was in between minus 2 and 2, so let's say if this was x of k for example, and it's going minus 2 and 2, the length here was 5 samples. And if we convolve it, it would be such that we'll go here minus 2, then minus 2, minus 1, then we keep on going, such as go minus 2, minus 1, 0, then minus 2, minus 1, 0, 1, and we keep on going as of such. Okay, maybe a 5 sample would be a little bit hard to illustrate. So let me use a 3 sample here just for clarity, to make my explanation a lot more concise. So this is like if we were going in between minus 1, 0, 1, x of k, and then if we had to do a convolution, when we do our slides, we'll be here at minus 1, then minus 1, 0, minus 1, 0, 1, and then we'll go such that it'll be 0, 1, then just 1. So in particular, that means we have 1, 2, 3, 4, 5 instances of sliding. So this here being 3 samples, when we formulate the length of y of n being the convolution of x of k here by itself, we see here that the length of x of k, so L x of k was basically 3 samples, and L y of n here was basically 5, because we had 5 overlaps here in particular. So in formulating an equation for this, this comes out such that L y of n is equal to 2 L x of k here minus 1, which is 2 by 3 here minus 1, gives us 5, which basically formulates our equation here for the length of y of n being up to 39 samples. So similarly, because we're trying to calculate for let's see, the index of the last non-zero value here in the convolution, what that means here is that we do have the length of y of n, and we know what the start point of y of n is. So we have the length of that, and start point of y of n was equal at y minus 11. We need to figure out what's going to be, what's going to be our final index. So let's go back to our general example here, right? Where we had our x of k here being 3 samples. So if x of k here was 3 samples, and we calculate our start point here, such that we know x of k here, for calculating the start point, the equation for that would have been start point for x of minus k plus the start point for x of k plus 1. So for our example here, so start point for y of n will be equal to 1 plus minus 1 plus 1. Just check this back to make sure the equation was correct on top. Yep, that's correct. So when we go here in particular, to give us 3, but because we're starting at a negative point, that's going to be minus 3 in particular. And we know that there's going to be 5 overlaps here because of the L of y of n. So that means we'll be going from y minus 3 to minus 2, minus 1, 0, 1, 1, 2, 3, 4, 5, right? Yep, so these will be our 5 parts here representing our length. So how do we make sure that we can calculate here to make sure that we get our final length here? Sorry, our final index here is going to be at positive 1. Knowing that we have the length of y of n and we have the start point for y of n here in particular. So we need to figure out, what's going to be our equation to map these two to get to the final point of y of n, right? So this is going to be what we're going to try and calculate for. Final point for y of n. And we know here that the final point of y of n is going to be at positive 1, right? So we need to make sure that we formulate an equation here to map the length of y of n as well as the start point for y of n, such that we can get to the final point of y of n. So if we watch here that we say, the length of y of n here, and then we're going to be adding the start point for y of n. That's going to be 5 minus 3 here, which will give us a value of 2, so we're off by 1. That means we're going to have to minus 1 here in our equation to make sure that we do satisfy that equation as of such. to make sure we get the correct start point. So in watching the equation here, for the final point of y of n, that's going to be the length of y of n plus the start point for y of n minus 1, to make sure that we do satisfy the equation here to get our final point here being at 1 when we manually evaluated it here. So if we go back to our actual question, and we know the start point of y of n here was at minus 11, and the length of y of n here was at 39 samples. So our final point of y of n is going to be equal to the length of y of n plus the start point for y of n minus 1. So this here is going to be equal to 39 minus 11 minus 1. So that's going to be 29, 28. This here is going to be at 27. And then finally for part 4, because we're going to be calculating for y of 27, these indexes here occurred at the final points here in particular, where we had minus 4 and minus 4 here. So that's going to be minus 4 all squared. Minus 4 multiplied by minus 4, which gives us a value of 16. Right. That basically gives us the correct solution here for question 5 in particular. And like I said, I scaled down the problem accordingly to explain to you guys how did we formulate these equations for calculating the start index and the final index, as well as how do we make sure that we prove that it was the correct thing here in particular, while formulating the equations in particular as of such. So when you do encounter these sort of problems, instead of tackling them up front, try using the scaled down version instead to see, okay, well, how can you manually evaluate what the final points are going to be and what the start points are going to be in particular. And then in formulating those, you can map back the equations accordingly to make sure that you do get to the correct values using the length and the start point here to calculate for the final point. The only key difference, the only thing that you need to pay attention to in calculating the start points is that you need to make sure that you do factor in this overlap when you're actually doing the convolution slides in particular. And the easy part is just to know what's going to be the equation of calculated for the start point of y of n. And the reason why we have it at a negative index, even though we calculate for the magnitude here just being 11, is that when we do start doing the slides for the convolutions, this here is going to be at minus 5, and this one here is going to be at positive 5. And if we consider these two here, a positive and a negative is just going to give us a negative in general. So that's why we have our starting index here going to be at minus 11 in particular. Let's say, for instance, if both of these indexes were negative, being that this was minus 5 here and the sliding index here was also minus 5 for some odd reason, that means a negative and negative will give you a positive. So that's how you end up getting a positive index to begin with when you're doing this. So hopefully that clears up anything in particular, but the solution presented here is the correct solution. I will make some adjustments on the PDF and put the correct solution as well on there and re-upload it for the problem set on solutions as of such. Any particular questions that I need to clarify, anything in particular that's a little bit unclear regarding the solution of question 5 here? Oh, part 4, yeah, sure. So part 4 here is that we're just going to be considering what's going to be, let's get back here, the value of the last non-zero value in the convolution. So when they ask for part 4 here in particular, they just want to know what's going to be the last values that are going to be convolving in particular. So if we jump back to our convolution signals here, out a bit. All right. Remember that when we do our slides, we're going to be starting at 5 here for x of minus k, and x of k here being our stationary signal, we're going to be starting at -5. So when we do our slides here in particular, when we now start, the value of 3 here is going to be multiplied by the value of 3. But then the last part here, when we're doing the convolution, it comes like that. This 14 here is going to be at -4, and this -14 here is also going to be at -4. So illustrating this, yeah, I'm going to have to draw this to illustrate what I mean, is that if we had our x of k signal here, x of k being at -14 and 5, here was 3, here was -4, and then we had, let me just draw here to illustrate the convolution, x of minus k, that slide across the entire signal. This here was going to be at -5, and this here would have been at 14. Now, because this is the flip version of x of k, -14 here now becomes +14, but this here value would have been 3, and -5 here now becomes -5 on the x-axis, but this value is going to be -4, and these two values here line up. So because those two values line up here for the last slide of the convolution, we just basically multiply these two values together. So that's how you get -4 by -4 for the last non-zero value of the convolution. And you just multiply the two and you get 16. Right, so the reason why we subtracted the 1 here in particular, let's go back to our generic example that we just now had here, right? So the x of k for this generic example only had 3 samples. And when we calculated for the start point of this x of k, it would have been 1 plus the magnitude of -1 plus 1, meaning that it would mean -3, right? And then because we know that the length of y of n, if we were dealing with this x of k here, would have been 2 multiplied by the length of x of k minus 1, we know that the length here is going to be at 5. We know the start point here is going to be at y of -3, so we need to figure out what's going to be our 5 values here, or 5 indexes. So we go -3, -2, 1, 0, 1. So these here are going to be 5 values. And we have the start point here, and the length here in particular, right? So we know from doing our manual evaluation that the final point for y of n here was +1. But in formulating the equation here, I'm going to rub this off here to show you why we need to put in that -1. If we say, okay, we have length of y of n here plus the start point for y of n, the length of y of n here was 5. So put in 5 here. The start point for y of n, when we did calculate it, was -3. That's going to be -3 here. So that's going to be 2, but this 2 here doesn't match up to our manual evaluation, because we can see here that was the final point when we manually evaluated it regardless. So the reason why we do put the -1 is really for the 0 overlap, like a colleague points out in the chat, also to make sure that the equation here is also satisfied for us to get the correct value. So we put -1 here. So as of such, we consider that zero overlap in particular. So we get back to our final point here being 1. So yeah, the reason for that -1 is really for the zero overlap that occurs. All right, any further questions? Oh yeah, sure. The equation for path 3 here is final point of y of n is equal to the length of y of n plus the start point for y of n minus 1. And that -1 was basically for that zero overlap. Alright, so the general trick when you do encounter these sorts of questions is they tend to be like really big in scale, and that is where a lot of people tend to get confused. So when you do encounter these sort of questions, scale it down to a manageable size, which is what I did here. Instead of dealing with the full question to begin with, I dealt with a very small amount of samples and then figured out, okay, how do I go about formulating equations using the small amount of samples in particular. And because I use a small amount of samples, it was easier for me to manually evaluate, okay, how do the convolution slides do occur and how many slides do occur as a result of it. So it's a lot easier for me to formulate this once we scale down the problem instead. And once I am able to formulate equations using the scaled down version, these equations here will translate onto the scaled up version or the actual problems that you're going to be dealing with. So that's the trick to when you're dealing with these sort of problems. Scale it down to a manageable size, and once you're able to formulate the equations using the manageable size, those equations can be transferred and used for any sort of size whatsoever. Once you have those equations, you can just basically solve for any sort of problem regarding any particular size in particular. I mixed up what I'm saying. Once you have these equations, you can use these equations for any size of this particular problem. They will be applicable no matter what. The only thing that you have to be very careful about is when you're calculating the start point, because like I said, the start point here, when we did calculate it for it, we need to make sure that we need to know what's going to be the sign of each one of these start points here for x of k and x of minus k. So because this here was positive for x of minus k, and for x of k was negative, a positive and negative will give us a negative. If both are positive, that means the start points are going to be positive. And if both are negative, that means the start point is also going to be positive, because a negative and negative will give you a positive. So just be very careful when you're calculating for the start point here in particular. That's the only thing to be concerned about. Once you do have the start point, everything else is just a matter of applying equations directly, and you'll be able to get all your indexes for the final point and the lengths accordingly for the sequences, as well as finding what's going to be the values at each one of these indexes in particular. Because for the start here, which was at -5 and +5, this is just 3 here and 3. And then for the last part, it's just going to be the opposite ones, which is going to be -4 here and -4 here accordingly. So the only thing to be very careful about is calculating for the start point. Once the start point is correct, all the other equations will just fall in naturally. Alright, so that basically brings us to the end of today's lecture. If there are no more questions regarding this, I mean, if there are any more questions regarding this, feel free to leave them down in the comments below. Hopefully I did address any uncertainties or any sort of things that anyone was unclear about with regards to this particular question, because I did get a comment on the video when I did it from before to redo it. So I basically figured out, okay, the solution in problem set 1 was wrong, so I actually did need to redo it. And like I said, I will correct the solution on problem set 1, and I will upload the solutions as such to reflect what I did here today. Alright, so next week's lectures in particular are going to be on the Z transform. Even though with that we did do the Z transform in signals and systems, we're going to have to redo it here in DSP, and in particular we're going to be using it for 2 different types of solutions, which are going to be referred to as the open form solution and the closed form solution. And we're going to be doing these in a little more detail as to how can we go about doing the solutions as of such. Also, there is a poll on my learning indicating which questions you guys wish for me to do live for problem set 2A next week Wednesday. And like I said, it's the same thing as before. Once you check off which 3 questions gave you guys the most trouble, I will do those live and explain how to go about doing them and clear up anything that you guys are not clear about regarding these questions. I will also upload problem set 2B, because I think we have already completed the material for problem set 2B, so I also put up a poll for that as well. Problem set 2B isn't as long as problem set 2A. I think there's only like 3 questions where you have to do manual working, and the rest is like the MATLAB application questions for you guys to actually play around with the signals in MATLAB and to see how they actually can be evaluated, getting some real world DSP application experience. So I will post up problem set 2B as well once I make sure that the material was covered, and I will also post up a poll indicating which questions you guys wish for me to do in problem set 2B that may have also given some trouble. But I can't really foresee any questions in problem set 2B given trouble. It may just require just a little bit of additional explanation. Alright, so next week's lectures are going to be the Z transform, and we will be doing problem set 2A and 2B in particular. Like I said, don't forget to vote on the polls which 3 questions gave you guys the most trouble, so I'll know in advance which questions to do live with you guys, and then as of such. Other things to note in particular, your midterm will be somewhere in March. I think it's in the 1st week or the 2nd week of March. Let me just verify this. See whether I did that. 7, so it should be in the 1st week or 2nd week of March accordingly for your midterm. And what I can tell you so far is that Your midterm will cover up to the end of lecture 8. If there are any changes, I will let you guys know in advance as to what it's going to be. Your midterm is also going to be I think the format normally used to be 1 hour and a half because it's online exams. I think it might be like somewhere between a 6 to 12 hour window instead to accommodate for any unforeseen factors such as if you lose power, if you lose internet and so forth. And it's going to be an open book exam. Typically it's only going to be 2 or 3 questions on the exam as of such, but as we approach closer and closer to it, I will be doing a little more practice questions as to what you can expect for what will come on the midterm in particular. So I'll make sure that you guys are prepared for the midterm in advance. And like I said, it's going to be a full open book exam, so you're pretty much set when you're doing the midterm. Alright, so until next week, take care, be safe, and I will see you guys soon. Later. Problem sets 1 and 2A in particular will help you prepare, and I think some of the questions in 2B will also be able to help you prepare as well. But if there's anything targeted, I will do additional questions accordingly and the solutions for you guys to prepare. And yes, up to and including lecture 8, so up to the end of lecture 8. Alright, see you guys next week. Later.